Hello, welcome to m253 Calculus 3 Cañada College. My name is Lapuz and I'm the instructor for the course. In this video, we will take a look at Stokes' theorem, section 6.7, theorem of Stokes. So Stokes' theorem relates a line integral with a flux integral. So not just a flux though, it's going to be the curl of a vector field. So it's the flux of a curl of a vector field, which is to say it's the integral of some derivative of a vector field that's going to be equal to a line integral. Now the flux is going to be taken over a surface, and the line integral here is going to be taken over the boundary of the surface. So it's the integral of a derivative of a vector field is going to be changed into a one less integral of the original function over the boundary. So if we start thinking about these theorems as an integral of a derivative over some object, and then it's going to be one less integral of the original function over the boundary of an object, then that's how we're going to move towards trying to make these relationships back to the fundamental theorem of calculus. So let's take a quick look at the geometry of Stokes' theorem. So again, it's a combination of a line integral and a flux of a curl. So the idea behind Stokes' theorem is that when we're looking at the circulation around it, the curl, remember, measures some sort of rotation. And as you're measuring the rotation, the curl gives you another vector that's going to be perpendicular to, remember, the right-hand rule of the curl gives you a vector that's going to be perpendicular to the surface. And then you're matching that up, you're dotting that with the vector fields that's going through the surface. And so that's how you're measuring the flux of the curl. Now, as you look at these curls that's happening on the surface itself, you kind of start to follow a particular movement towards the boundary. So if you take a look at the curls that's happening here, you can kind of stack a couple of sub-partitions together, and you see the curl of the bigger picture. And then if you see these things right next to each other, you can see the curl happening and enlarging out. So in other words, the curl that's happening in the first picture here kind of establishes a circulation around the edge or the boundary of the particular surface. And that's how you can make your relationship between a flux through a surface, a flux of the curl through a surface, with a line integral over its boundary. And there's a few ways to use Stokes' theorem. Generally, with Stokes' theorem, we don't know which is going to be the easier way. So there's a lot of times when we go from a line integral to a flux integral, there's a lot of times where we're asked to do the flux of the curl and say, oh, that actually computing the flux integral might be a little too tough, so let's just go move towards the boundary. And so one of the things that we can do is that, for example, one way to use Stokes' theorem is that if you have in this first picture on the left, if you have an intersection between the two surfaces, and you want to find the line integral over that intersection, well, the line integral is kind of tough to see. So maybe we can instead do the flux of the curl of a surface. But what's that surface look like? Well, if we take a look at the intersection between these two, it's just going to be that curve. And if we take out the cylinder part of the picture and just look at the part of the picture that's within the cylinder, and now we have a surface that we can deal with. So if we could take the flux of the curl over the surface, that might be more manageable than trying to parameterize the curve itself, which may not be so easy. Another way to use Stokes' theorem is that if you want the flux of the curl through this big surface, well, you can exchange that to just the line integral over the boundary of the surface, and so that line integral isn't going to be so bad. But if you find that the vector field that you're integrating is a little bit more complicated than you want, but the curl of that vector field might be easier, maybe you can replace the big surface with a flatter surface as long as it has the same boundary. Then it's going to be equivalent. So what we could do is we can imagine going from a flux of a curl of a surface to a line integral over the boundary to a flux of a curl of a simpler surface. So that's to say that the flux of a curl over that cornucopia looking surface is exactly the same as a flux of the curl of that disk that we use as a cover. And so maybe that might be easier to integrate the flux of the curl of that instead of the flux of the curl of something, some complicated surface. So those are a couple of ways to use Stokes' theorem. But in general, we're going to be looking at this, so we're going to be computing at this, and sometimes it's easier to use the line integral, sometimes it's easier to use the flux integral, so it just kind of depends on the problem. Some problems will ask you to do both and compare and make sure you get the right answer, but other problems will ask you to do one or the other. All right, I hope that helps, and practice with Stokes' theorem. And then you'll get to see and feel the relationship between the original fundamental theorem of calculus. Okay, I hope that helps.